Alright, so this video marks the start of our new chapter on exponential equations. And an exponential equation is going to be an equation where our variable is actually in the exponents. This is something that to this point in our class hasn't occurred. Typically, the form you'll see them written in is like this: y equals a times b to the x power. A and b are just numbers. They're constants that we're usually given in the problem. And x, the variable we plug in for, is actually up here in the exponents. So let's take a look at an example, and let's look at what the graphs will look like. Here we have y equals 2 to the x power. In terms of exponential form right here, you could think about this. It's really 1 times 2 to the x. So the number by itself out front is a 1, but that's not terribly important here. And I went ahead and made a table for this. If you plug in a 0, you have to do 2 to the 0 power, which equals 1. If you plug in a 1, 2 to the first is 2, 2 to the second is 4, 2 to the third is 8, etc. And you can see right here, kind of the exponential graph that we will get is over here on the right. And the exponential's claim to fame is that it grows really quickly once it gets going. Out of all the graphs that we will cover in Algebra 2, exponential graphs are by far the fastest. I went ahead and included what happens when you plug a 10 in here. 10's not even that big of an input. It's like, okay, that's much farther. It's already going to be at 10 comma 1024. And if you were to plug in 11, you would be in the 2000, it'd be 2048. So it's just incredibly fast growing here. So, first of all, I want you to write that down. Exponential equations grow faster than any other type of graph. So exponential equations, let's say, change faster than any other graph we'll cover, or any other type we will cover. So this graph really just takes off right here. The next point, if I would have included it, would have been 6 comma 64. What this graph is essentially doing is every time you move over 1, the x value in this problem doubles, because you're raising 2 to 1 more power, which means you're multiplying by 2 again. Back in chapter 6, when we did polynomials, we did that finite difference thing, where we looked at how much you add or subtract to get from one number to the next. With exponential equations, that wouldn't work. Like, you would never get the same number, but you end up multiplying by the same number over and over. It's always times 2 here. One more thing on this slide, I know I've kind of said a lot about it. This is an example of exponential growth. Because our graph is growing as we go from left to right here. It's going upwards here. It's exponential growth because b, the number you're raising to the power, is greater than 1. So b is bigger than 1. If you have like a number that's bigger than 1 right here, your answer is going to get bigger. It's growing as we go. We're going to look at a second example. So this example right here, we have 27 times 1/3 to the x power. So this time our b here is a fraction between 0 and 1. And as a result, when we actually graph this, you can see I plugged in some points right here. Our graph is going downwards as we go along here. This is an example of exponential decay. And those two vocab words will be important, being able to keep them straight here. It's exponential decay because b is between 0 and 1. In other words, b is a fraction that's going to be a decimal between 0 and 1. Which means when you graph this right here, if you keep, when you raise the power here, you're going to multiply by 1/3 again, and again, and again, and again. When you multiply by 1/3 repeatedly, your answer is going to get smaller. Notice on both of our graphs right here, these are just two examples, our graphs are really steep on the one end, but they seem to pretty much taper off and level off on the other side. So here, this graph starts out really high, and it's just going to keep on going upwards like that. But on this end, it's already pretty much leveled out to basically 0 right here. And in this graph, it never actually will reach 0, because no matter how many times you multiply by 1/3, like if I did 1/3 to the 500th power, however many times I multiply by 1/3, I'm never going to get 0 for my answer. It's just going to be a really tiny decimal. On the last example, the same sort of thing happens on the other side. If you start plugging in negative exponents here, you're going to get really tiny decimals until your calculator just gives up and pretty much rounds them to 0. But exponential graphs have this tail side that levels off, That is an example of something called a horizontal asymptote, which is a vocab word I'm pretty sure you would have not have heard to this point. A horizontal asymptote is a value that your graph actually levels off to. So you saw both of our examples had tails. The graphs kind of tailed off at a certain value. Nothing we've covered in our class to this point has a horizontal asymptote. This is the first time we've seen one. And if you don't translate your exponential function, it will have this kind of tail at y equals 0. And again, we saw that in our examples there. Both of those graphs tailed off at 0. So in our next video, we're going to learn how to learn a little shortcut that will make graphing exponential equations really quick.